In this video, I'm going to go over the analysis of this half-wave rectifier with a resistor and inductor load. Now, the purpose of this circuit is that we have an AC voltage source, and we want to produce an output voltage that has a DC component that's non-zero. Now, we have some questions that we want to answer. What does the current through this circuit look like? And what is the waveform for the output voltage? So to answer these questions, we're going to start from the beginning. As the input voltage source goes from zero and starts to rise a little bit positive, we're going to have the diode start to conduct. And when the diode conducts, we're just going to model it with a short circuit. Then our circuit is going to look like this. With the diode shorted, we're just going to have the voltage source directly connected to the series load of the inductor and resistor. So now we want to find the current through this circuit I. Now I can be written as the forced response plus the natural response. The forced response is the steady state of the circuit. So after any of the initial natural responses have decayed. So to start by finding the forced response, we're going to use some phasor analysis here. So Vs, as you recall, is Vm sine omega t. So this is going to be equal to the real part of the phasor, and its phasor is just Vm angle omega t. And now we want to write the phasor form for the series impedance of the resistor and inductor. So let's call this Z. So Z equals R plus j omega L. And this is going to be equal to the real part of the phasor of the impedance. Now the impedance phasor is going to have a magnitude of R squared plus omega squared L squared. This is the distance of this complex value from the origin. And the angle is going to be equal to the arctangent of omega L over R. So now we have, let's call this magnitude of Z, and let's call this angle of Z theta. So now we want to find the force response IF. And IF is going to be written as the real part of the phasor of Vs over the phasor of the impedance. So this is going to be Vm over angle omega t over magnitude of Z angle theta. So this is equal to the real part, and now the magnitude is just divided by each other, and then the angle is going to be omega t minus theta. So this means IF is the real part of this, so we're going to get the sinusoid of omega t minus theta. So it's equal to Vm over magnitude of Z sine omega t minus theta. So now we have one part of our answer to the current, which is the force response here expressed. So the next step is to find the natural response. The natural response is due to just the inductor and resistor themselves and their dynamics. So in this case, we're going to zero out the voltage source to find the natural response. R, this is L. So by KVL, we're just going to have the voltage drop across the inductor plus the voltage drop across the resistor equals 0. Now VL is L d, let's call this IN flowing through the circuit, L din for dt, so the voltage drop VL, plus VR, which is going to be R times IN. And this has to be 0 because of KVL. Now, just by inspection, we're going to expect that IN can be expressed as an exponential. In this way, the derivative of an exponential is just an exponential. And in that case, we'll have these terms cancel. So IN is going to be in the form of an exponential with a coefficient a that we don't know yet, and a time constant tau that equals L over R. So this is the form of the natural response. So we found the forced response clearly, but we're still missing the coefficient for IN. So let's write out the total response expression. The total response is IF plus IN. with IF equals Bm over Z sine omega t minus theta plus In is AE negative t over tau, with A being an unknown. So at this point, because of the natural response, we need to use the initial conditions. So let's use the initial condition that initially, right when we turn on the source, going from 0 to a positive value, the current at this point must be 0. There's no current flowing through the inductor just yet. So I0 equals 0. So now let's plug in t equals 0 into our expression. So Bm over magnitude of Z sine omega t is 0, so then we're just left with negative theta plus AE negative t over tau. So it's just going to be AE to the 0. AE to the 0 is just 1. So now what we want to do is we see that A is just equal to this expression brought over to the left. So it's equal to, so we're going to get a negative sign when we bring this over, but then we already have a negative sign due to this negative theta. So then it's going to be a positive Vm over Z sine theta. So we found the value of A. Thus, we can write that the total current I, this is when Vs, the source voltage, goes from 0 to a little positive value. We're going to start getting a current. And the current expression now is I equals IF plus IN, and then Vm over Z sine omega t minus theta plus Vm over Z sine theta E negative t over tau. Now we can factor out Vm over Z. That's going to give us, inside the parentheses, sine omega t minus theta plus sine theta E negative t over tau. So we found the expression for I. So now that we found the expression for the current, let's go back to the waveforms and draw it out. So here's our circuit, and we found the expression for I just at the beginning as Vs goes from 0 and becomes positive. So it turns out that the waveform for I looks something like this. Now, the waveform for I looks like this, but what happens when it starts to come down to 0? Is it going to keep going negative? Well, our expression shows, yes, it does get negative. But what happens in the circuit with a diode when the current wants to become negative? Well, the diode's going to prevent any current from going this way. That's the nature of the diode, that it does not allow current to conduct in that way. So the diode's going to turn off once the current tries to go the other way. So the diode's going to turn off and become an open circuit. So that open circuit means that once it tries to go negative, there's going to be no more current. So at this point, we're just going to get the current flowing through the circuit is 0. There's no negative current in this circuit. And then in the next cycle, we're going to get just periodic repetition. So it's going to look something like this again and go back down, at which point it reaches 0 and is 0 again until the next cycle starts, at which point it will begin to rise again. So let's label this green waveform as the current going through the circuit. Now, what happens to the output voltage? So as there's current conducting in the circuit, then the diode is modeled as a short circuit. So that means if this is a short circuit, then the output voltage is just going to track Vs because it's connected to the same node in the circuit. But when it becomes an open circuit, what happens? When it becomes an open circuit, Vd is going to have to block Vs because of KVL. So then at that point, Vd is going to be blocking all of the voltage from Vs while Vout is going to be 0. And that also makes sense because when the current is 0, the voltage drop across the resistor is 0. And because the current is not changing, di dt is 0. So the voltage drop across the inductor is also 0. So that means our output voltage is going to look something like this. So when there's current, Vout the diode is a short and Vout is just going to track Vs. But at this point, when there's no more current, zero current, the diode's an open. Diode is an open, so Vout is just zero. Vout is just zero. There's no voltage in the circuit at the output node, I mean, and we're going to just get zero voltage. And once again, when the next period starts, we'll see the same thing. Once it reaches zero, the output voltage is zero. So this red waveform is Vout. So then what does the diode waveform look like? So when it's conducting, it's just a short circuit. So there's no voltage across a short circuit. But when it's an open circuit, we know that it has to be equal to Vs by KVL because Vout is zero. So when the current is zero, it's going to track Vs. So this purple waveform, is Vd. So let me just draw the waveforms a little bit thicker so it's more clear. So this is our current through the circuit. And then our output voltage in red follows this trace. And then Vd in purple is our diode voltage. So we can see Vd plus Vout is equal to Vs, and that makes sense by KVL. Vd plus Vout is equal to Vs. And note how this point is a key point right here. The point that the current through the circuit drops to zero. And this point is called the extinction angle beta. So this is the point that we get the state of the diode changing. Now to solve for this point, we can set the value in our expression for the current at the time omega t equals beta. That expression is zero. So for this value, so first we want to express I of t in terms of omega t instead of t. So that just means here we add an omega right here, negative omega t, which means we also need to divide by omega tau. So now our current I omega t is expressed just by adding that omega there. It's just multiplying by omega top and omega on the bottom. So at omega t equals beta, this is the point that the current drops to zero. So this expression, plugging in beta, gives us zero. Sine, so omega t is beta, so beta minus theta plus sine theta. E negative omega tau, so E negative beta divided by omega tau. So this is the expression we can use to solve for beta. Now, there's no closed form solution for beta here, so you need to use some type of calculator program with numerical methods to numerically solve for the value of beta. You can also use a circuit simulator like LT-Spice with your circuit to find beta in your waveform. So with this value of beta, we can write out the complete expression for the current in the circuit. So I omega t equals, for the period from 0 to the extinction angle beta, it's going to be equal to Vm over the magnitude of z times sine omega t minus theta plus sine theta e negative omega t over omega tau. And this is for the interval from 0 to beta. Otherwise, as we know, the current wants to go negative, but the diode's not going to let it go negative. So the current through the circuit is 0, and that's otherwise, which is also beta omega t 2 pi. So, and let's also recap the magnitude of Z we had found is the magnitude of the impedance. The angle is inverse tan of omega L over R. This is just our complex math. And then the time constant, our natural response, is the inductance over the resistance. So this is our key expression for the current through the circuit. And note that this expression here is used to solve for beta. So going back to the circuit we analyzed here, like a key takeaway is the characteristic of the diode. So in this case, once the diode started conducting, because it's not a switch we directly control, rather the switch is controlled by the voltages and currents in the other parts of the circuit. So once the input voltage source starts to rise from 0, the diode begins to conduct. At that point, then, the diode's out of the picture. Then it's just the voltage, resistor, and inductor, and the current flowing. So once the current begins to flow, we get the sum of the force and natural response of the circuit, giving us the waveform for I. However, at the point where the current wants to begin to go negative, we get to beta, the extinction point. So this extinction point means that the diode will stop any negative current. So the diode does play a key role here in determining our waveforms. So another thing to note is the voltage drop across the resistor VR. So VR is just equal to I times R. So that means it's just a scaled waveform of I because R is a constant value. So VR is going to look something like this. It's just a scaled copy of I. Start begins to rise once it gets positive, so on. It's just following the shape of I. So this is VR, and because VR plus VL equals V out, because we know the waveform of VR, the waveform of V out, we can also proceed to find the waveform for VL. And you can do this on your own and also try it out in simulation. So overall, we've analyzed the circuit. We found the expression for the current I, as well as the output voltage V out. So I hope this video helped you to further your understanding of this half-wave rectifier with RL load. And if you hope to see more content like this in the future, please subscribe and give a like. Thank you.